Welcome to solverfy.
We have another case here of a block suspended from a spring. This time the spring has a stiffness of 600 newtons per meter. The block has a mass of 7 kilograms, and the damper has a damping coefficient of, let's see here, 50 newton seconds per meter. We're given some initial conditions. Initial displacement is 0 and initial velocity is upwards, and we're measuring y as down. From this information, we can figure out the natural frequency and the damping ratio. Let's see here. Then we can figure out the damped natural frequency using the expression given in the book. And that should always be less than the natural frequency, and we can see that that's so. It's 8.54 radians per second compared to 9.26 radians per second. Now, the expression for free damped oscillations is like this, and you can see that the difference basically is that we have this, oops, I forgot a T in there. We have this exponentially decaying term here. So we have exponentially decaying oscillations that have some amplitude. And so we have things that oscillate and then decay and eventually get very close to zero as this thing gets very close to zero. So we have our initial conditions. Y at 0 is, well, that's e to the 0 is 1, and this is 0. So we have sine of phi, well, times d equals 0, but d isn't going to be 0 because that would be the trivial solution and not satisfy this initial condition. So that says phi has to be 0. So in this case, we have 0 phase in our solution. Now, we can take the derivative of this, and I didn't go through that mess because we can just use a bunch of product rules, and it simplifies down, but it's just calculus. Take the derivative of this, set t equal to 0, and you get, and plugging in the values, you get 8.542 times d, and that must be the initial velocity, which then tells us that d is minus 0.0702 meters. Plugging that into here and using phi is 0, this is what our expression looks like as a function of time for the motion of that block. And we can see here that it decays fairly rapidly. After 1 second, e to the minus 3.5 is pretty small. So it decays fairly rapidly, and our damping ratio here is greater, well, is less than 1/2. But any damping ratio that's greater than like 0.1, the things are going to decay pretty rapidly. In most structures, the damping ratio is usually they're talked about in percentages, like 5%, which would be 0.05. So once you get over like 0.2, 20%, you really don't have much oscillations. It dies out very rapidly.